Does anybody have any questions from worksheet 1?
Yes.
Okay.
Could we do number 4, please? What do you want?
Sure. No problem. So here we're just foiling this stuff out. So 2x times x, 2x squared, 2x times 3, 3x. Negative 1 times x is negative x. Negative 1 times 3 is negative 3. Combine our like terms there. That's all she wrote.
Oh,
just foiling. Yep. I don't know. So I'm just asking to expand, so it's just foiling.
Well, can we do number 5 then?
Sure. Same thing though.
Oh, okay.
Right? So like cosine x times cosine x is cosine squared x. Remember we write the squared here.
I was not starting out.
Whew.
On a paper towel.
On a paper towel. This must be from Miss Llewellyn.
Yeah, cleaning up.
Gotcha. Okay. I'll make sure to change that because I know you have like
14.
How many?
14. I can't say one more. I don't have it Saturday. Second.
Oh, they're not letting me change it now. Why aren't they letting me change it?
Yeah, you're done, bro.
Yeah, I don't know. Send an email to attendance.
Me?
I guess I could do it. That's fine. I'll do it then. I don't know. I don't know why they locked me out of it. Maybe I should just start.
Do you miss classroom?
Well, I miss the being able to update those things a little bit more easily. What hour is this? Is 7th hour. All right. Anyways, continuing on here, Joe. So, oops. Cosine x times negative 1, that's just negative cosine. 2 times cosine x is 2 cosine x. And then 2 times negative 1 is negative 2. These guys are like terms, so we just add their coefficients. And I put a 1 there. Coefficient, that doesn't really need to be there though, obviously. But still just the same thing, right? No big deal. Sydney, did I see your hand coming up earlier, or was it Claire?
Oh, it was
Oh, okay. It was quick and it was brief, but I saw it and I couldn't. 5 minutes later, I couldn't remember whose it was, but it was coming from that corner. Jay. 14? Sure. So the first thing that we'd want to look for is a greatest common factor. So if I look at the coefficients first between 28, 16, and 80, the greatest common factor there has to be just 4 at most, right? Because the 28 is 4 times 7, and certainly 7 doesn't go into 16 or 80. So it's at most 4, and surely 4 goes into 16 and 80 also, right? Yes, Rami?
Okay, I was just going to... Oh, okay. We're going to have to take out a 4y or just a 4.
Yeah, we're going to take out actually a 4y squared. If we look at the variable parts, and they all have at least a y squared in them. So that's our first step. Cool so far, Jay? Okay. 3 terms, clearly. In the quadratic form, pretty clearly. Leading coefficient isn't 1, so it's going to be the long factoring problem. So what we're going to do is we're going to look for the 2 things that multiply to give us the leading coefficient times the constant term, and then add to give us the linear coefficient. Great. So Rami's identified that negative 10 times 14 multiplies to give us negative 140, and also adds to give us 4. Now keep in mind that does not tell us how to factor this immediately. What that does do is it tells us how to break up the linear term. So instead of writing 16y, 16y, I'm working from the one in parentheses, you dummy. I'm going to write, instead of writing 4y, I'm going to write negative 10y plus 14y. And then I'll make my 2 groups. Note that when I make those 2 groups, I have to have a plus sign in the middle. So if you had written that as 14 minus, or 14y minus 10y, just make it plus a negative 10y, and it's fine. From the first group, all we can take out is a y. That's our greatest common factor. From the second group, we can take out a 2. And now, since each of these contain a 7y, 7y minus 10, I can take that out. That leaves me with y plus 2 left over. But don't forget about that 4y squared that we had taken out in the beginning. Easy to kind of forget about that, guys. We haven't thought about him in a minute. But that makes him sad, right? Why is no one thinking about me? I was really important in the problem a little minute ago. And that's the end there, Jay. Does that feel okay? Ariana? Okay. So again, we talked about that the cosines we can just kind of think about as a variable. So like if I think about A as the same thing as cosine y, this is really the same thing as like a squared plus 2a plus 1, right? Okay, no greatest common factor. 3 terms in the quadratic form. Leading coefficient is 1. So all I really need to do is find 2 things that multiply to give me 1 and add to give me 2. Those 2 things would just be 1 and 1, right? There's only a couple of numbers that multiply to give us 1. So because the leading coefficient is 1, that's actually going to take me straight to my factored form. I don't have to do that grouping step. And then my last step would be to just put the cosine y's back in there. So every place where there was a y, I'm just going to replace it with a cosine, or every place there's an a, I'm going to replace it with a cosine y. And that's all we got. And just FYI, like, you don't actually have to do this substitution, like make it equal to a if you just can see the cosine y as a variable the same way you would see like an a or a b or whatever. You don't have to make that substitution. When I introduce this, though, typically I do just so it's easy to see that I'm going to treat that just like a variable. But after you've done it a couple of times, usually people are good with just forgetting about that substitution and just leaving everything the way it was, which is fine. All right. Last call from this set before we move on. Okie dokies. Today we're going to do 5.1 for real. Ooh. So in section 5.1, we're going to be talking about our basic trig identities. So when we say identity in a math class, basically all we're talking about is like an algebraic statement that's like always true. So like, I don't know, something silly like 2x plus 6 equals 2 times x plus 3. You could count as an algebraic, or it could count as an identity since like that's something that's true. It's kind of a silly thing to call an identity, but like that's always true. Sure. Today what we're going to do is we're going to develop a whole mess of trigonometric identities. Now a lot of these things are things that we've already kind of made mention of, or that we've already kind of like have the basis for these ideas that we've already talked about. We're just kind of formalizing them now. And then we'll do some examples of the kind of problems we'd be using these to do. Okay? Oh, good. So we're going to start first with the reciprocal identities. So you guys remember that like sine and cosecant are reciprocals, cosine and secant are reciprocals, and then tangent and cotangent are reciprocals. So let's formalize those into equations. So we can say that sine is equal to 1 over cosecant, or we could say that cosecant is equal to 1 over sine. And I should be saying like cosecant theta equals 1 over sine theta. I just have a bad habit of just dropping the variable name when I say it. I always write it, but sometimes when I'm talking, I get going too fast and I forget to say those things. Everybody's okay with these? Okay. So we can do the same thing for cosine and secant. So cosine theta is equal to 1 over secant theta, or secant theta is equal to 1 over cosine theta. And then tangent and cotangent, the same relationship exists. So tangent theta equals 1 over cotangent theta, or cotangent theta equals 1 over tangent theta. Okay with that? All right, so that's our first set of identities. Our next set is going to come from kind of the unit circle setup. So remember when we described the unit circle, if I pick some point xy on that unit circle, I can make a right triangle where the horizontal side is the x coordinate, the vertical side is the y coordinate, and then that hypotenuse is the radius for the circle, right? Everybody agree with that? That's just a circle, right? So the Pythagorean theorem says that a squared plus b squared equals c squared. So in our case, x squared plus y squared is equal to r squared. On the unit circle, the x-coordinate is cosine, the y-coordinate is sine, and the radius is 1. So that's going to become the first of what we're going to call the Pythagorean identities. Are we okay there? We can develop 2 more versions of this. So if I had taken this Pythagorean identity and divided both sides by cosine, oh shoot. Got to do a set. Uh-oh. Time out. We're going to go up here. We'll come back to that in just a second. We didn't do the quotient identities. My apologies. This will be a quick one, though. There's only 2. So on the unit circle, you remember that tangent is y over x, right? And on the unit circle, y is sine and x is cosine. So we can say that tangent theta is equal to sine over cosine. And then similarly, if cotangent is the reciprocal of tangent, cotangent must be cosine over sine. Everybody okay there? All right. So back to here, when I so rudely realized that I had forgotten to do something. So we had that Pythagorean identity, sine squared plus, or cosine squared plus sine squared equals 1. I divided both sides by cosine. So cosine squared divided by cosine squared is 1. Sine squared divided by cosine squared is going to be tangent squared. And then 1 over cosine squared is secant squared. So that's our second Pythagorean identity. Just a different version of sine squared plus cosine squared equals 1. Or, let's say again, we're starting with sine squared plus, or cosine squared plus sine squared equals 1. And this time maybe we'll divide both sides by sine squared instead. Cosine squared divided by sine squared, well, that's cotangent squared. Sine squared divided by sine squared is 1. And 1 over sine squared is cosecant squared. So that's going to become our third Pythagorean. Our next set is called the cofunction identities. And to talk about these ones, I just want to go back and refer to the unit circle for a moment. So have you guys noticed on the unit circle that, for example, sine of 60 degrees is 1/2? Or sorry, sine of 30 degrees is 1/2. And cosine of 60 degrees is also equal to 1/2? That these values for sine and cosine repeat like that? Do you notice there's any relationship geometrically between 30-degree angle and a 60-degree angle? Is there a special geometric relationship between a 30-degree angle and a 60-degree angle? Yeah, it's a special word that you learned in geometry. It starts with a C.
Congruent.
It's not congruent.
That would be the equal.
That would mean they were equal, which they're definitely not.
Converse. No. I don't know.
CO
CO.
M
Converse.
P
Comparison.
complementary.
Oh, complementary angle.
That means they add to give us
90.
90 degrees, which is what those are doing. So what we're seeing is that if I take sine of an angle and cosine of the complement of that angle, they're equal. Right? That's what these next cofunction identities are going to be describing. So sine of a complement is equal to cosine of that angle, and the vice versa is true. So remember that pi over 2 is just 90 degrees in radian land, right? So pi over 2 minus theta and theta are complementary by definition, right? So I take sine of an angle and cosine of its complement, they're equal. That's all we're saying here. Yes, of course. If this is true for sine and cosine, it's also true for secant and cosecant. And if it's true for those, it better be true for tangent and cotangent. And here's a fun fact. So you notice that the names for these trig functions, sine, cosine, tangent, cotangent, cosecant, secant, 3 of them start with the prefix CO, right? The prefix CO is short for complementary. So sine and cosine are complementary functions because sine of theta is equal to cosine of the complement of theta and vice versa. Secant and cosecant are complementary functions because secant of theta is equal to cosecant of the complement of theta. And the same thing with tangent and cotangent, complementary functions. So the naming convention for our trig functions reflect these identities that we've just written down. Okay, the last set here for us are the odd-even identities. So these odd-even identities are going to be relying on this property of odd and even functions that we discussed way back in the first chapter. Does those look vaguely familiar? It's been a minute. Okay, so we have this. Now remember back when we talked about graphing in chapter 3. You remember all the way back to chapter 3. We said that sine was an odd function then. Since sine is an odd function, we know then that f of negative x is equal to negative f of x. And if sine is an odd function, then its reciprocal is also an odd function. So cosecant of negative x is equal to negative cosecant of x. We said that cosine was an even function, so f of negative x has to equal f of x. And if this is true for cosine, it better be true for its reciprocal, secant. So secant of negative x is just equal to secant of x. And we said tangent was an odd function. So tangent of negative x is equal to negative tangent of x. And its complement, its reciprocal also has to be an odd function. So cotangent of negative x also equals negative cotangent of x. So these identities that we've talked about here today are basic trig identities that we're going to be using to do the assignment for this first section. I've typed out and put all these identities in one place for you. If you look at the basic trig identity sheet inside the content library, I have all the identities typed up in one location for you, so you don't have to go hunting through notes to find them. This is not something we'll expect you to memorize. Okay, so I would give you these to work from for the test. Yeah. Should you eventually probably memorize these things?
Probably.
You'll probably end up memorizing a lot of them because you'll use them pretty frequently. Now, do you have to have all of them memorized? Or would you? Probably not. But I'll tell you what, the assignments or the problems in this section will go a lot quicker and a lot easier for you if you have a good chunk of these things memorized. Just real talk here. Okay. So let's go run through some examples of what exactly we're going to be doing in the homework here. So what I'm looking at right now is the thing titled Notes 02. So we're going to run through some of these examples here as a group. The directions here say simplify the following expression. When we say simplify, what we want to do is take this expression and find an equivalent expression that's simpler. So when we say simpler in mathematics, if something has 3 terms, if you can make it turn into 2 terms, that would be simpler. If your thing contains the product of 4 things, if you can rewrite it so it's the product of just 3 things, that's simpler. Everybody kind of have a notion of what we mean by simpler? So like if you have 2 fractions that are being added, simpler would be to add the 2 fractions to get 1, right? If you have 2 things dividing each other, would be to divide them to get a single quotient, right? Like we're just trying to get things to be simpler. Now we want to do all the simplifying we can. So like the most simplified thing you could ever get to would be a single number. If you can get this thing to simplify down to like 5 or 7 or 8 or 2 or 0 or 1 or whatever. Sometimes that'll be possible. Not always. The next simplest thing is if you can get down to a single trig expression. So it just involves one thing like sine or cosine. That's, often will be the case where you can get it down to a single trig function. The next simplest thing is if you can get it down to like a single term. So maybe it's the product of two things, like sine times cosine. And occasionally the simplest you could get it is just to like 2 terms or 3 terms, or you might end up with like sine plus cosine. There's nothing more you can do to that. That's as simple as that could get. But those are examples of like what a fully simplified answer might look like. So it's not always going to look the same. So our tools that we have available to us to use to do this simplifying, we have algebraic tools. So things like factoring or foiling or adding fractions, making a common denominator to add fractions, reducing fractions. These are things that are available to us. We can use any of those tools that we developed last year in our Algebra 3-4 class. Our second set of tools are these trig identities that we've just discussed. Most of these problems will involve using some of each of those sets of tools. This is why we started the chapter with some preliminaries and reviewed like some of these skills that we would have worked on last year that we're going to still have to use, like factoring and foiling and stuff. Okay, so let's look at the first example and work through this kind of together. The first thing I typically look for is I look to see if there's any algebraic things I can do. So let's look at sine cubed x plus sine times, sine x times cosine squared x. That's our first example. Does anybody see anything algebraic I can do there? Is there something I can foil or factor or make a common denominator with? You can't foil it because it's clearly not set up as the product of two parentheses, right? So I can't add the signs because, well, one is a sine cubed and the other is a sine. But in addition, the sine has a cosine squared attached to it, right? So they're not like terms at all.
Well, can we find a common denominator?
Well, they have a common denominator. The denominators are both 1. What if we write it this way? What if A is sine and B is cosine? If I think about it this way, do you see anything?
Okay, so it's not distributing.
What's the opposite of distributing? That's factoring a greatest common factor, right?
Yes.
Notice that each of these terms has an A in it, right? So we can factor off A.
Oh, we factor up sine.
A greatest common factor of A. So here, they both have signs on there. We can take off a sine x. Everybody okay with that idea? So when I take out that sine x, what's left? Sine cubed becomes sine squared. And sine x times cosine squared becomes just cosine squared, right? Is everybody okay with how we did that? Okay. So I'll look again. Is there any algebraic thing that seems obvious to do here? Well, I mean, I could distribute the sine x back through, but that's dumb because it just Goes right back to what I started with. I don't see anything.
So it's the simplest form.
Nope. Now we're going to go and look at our identities. So we're going to look at our identity sheet and see if there's anything that involves sine or a sine squared or a cosine squared. And there is a particular identity that should leap right out at you that would be an excellent one to use in this case.
Identities.
Here, let's do this. In red is what we're working on. That was not complete. There's still more to do.
We use P1. Yeah.
Right? In our problem, we have a sine squared plus cosine squared. So I can use P1 to replace that with 1.
Is that like the normal objective? Like try to find one of the identities?
Yeah, the typical route on this is you'll try to do some algebra stuff to combine things or like to factor something or to whatever. And then we'll end up having to go to the identities and find something that'll get stuff to cancel or get smaller in this case, right? Like we got rid of a sine squared and a cosine squared with a 1. It's a pretty good deal, right? That gets things awful simple later. And then once we've gotten down to a single thing, we know we can't do better than that, right? Okay. Let's look at this second example here. So we have secant x minus 1 times secant x plus 1 all over sine squared x. Again, I typically start by looking for anything algebraic to do.
Well, we can do
Yeah, right. We have two parentheses, two binomials plopped next to each other. Screams FOIL, right? Notice that in this particular case, we have like a difference of two squares thing to FOIL, like an a minus b times a plus b. You guys see that? So I'm going to use that difference of two squares factoring pattern to just do the multiplication really easily. Now you could still have FOILed that out and you'd end up at the same spot. I'm just using that as a shortcut so I don't have to do as much writing. Is everybody okay with that? Okay. Any other algebraic things to do here? What do you guys think? Doesn't look like it, right? I mean, you could factor secant squared minus 1 as a difference of two squares, but it just takes you back to what we were at before, which I'm not really interested in doing that, right? This is clearly, it looks a little bit simpler than where we were at before because it has less stuff in there. Okay, so what do we do after we've done that? If we've exhausted all the algebraic things to do,
check our
go to the identity sheet. So I'm going to be looking for things that involve secants, secant squareds, sines, or sine squareds, right? Because that's what I have in here. So if I go and I look at this, does anything jump out at you?
Was this sine over sine? No.
It was 1 minus, or secant squared minus 1 over sine squared.
squared times 1 over sine times 1.
It was secant squared minus 1 over sine squared.
It's got to be something in there.
I would use this one. I'm going to replace the secant squared with the tan squared plus 1. Well, secant squared is equal to tan squared plus 1, right? So that's what I'm going to do. And watch what's going to happen here by doing that. So where the secant squared was, I'm going to write, tan squared x plus 1. I still have the minus 1. And now we're over sine squared. Right, so I did that. Was the substitution I made from the identities. Why was that a good thing? A plus 1 and a minus 1 had to give me 0, right? No, but it's better than it was, right? Because now we don't have any more addition and subtraction. We're just down to a single fraction. That's better, right? So for the next step, what I'm going to do is a trick that I often will employ that I'm just going to kind of tell you about. Instead of thinking this as tan squared over sine squared, which is what I have left, I'm going to think about it as tan squared times 1 over sine squared. Now, why would I want to do that? Yeah, when I go to the sheet, I'm going to look for something to use tangent, but I want something that's going to turn it into a fraction. Specifically, I'm going to use that one. Now, notice that I have a tan squared, and this is for a tangent. Does that make a big difference?
I guess not.
I mean, I'm just going to say that tan squared is equal to sine squared over cosine squared. I just have to keep the exponents, consistent. But why was that going to be beneficial?
What is it called? Cross.
That's just reducing is all we're doing right there. Yep. Yep. What do we get when we do that, reducing? 1 over cosine squared, right? Important that you remember to keep the 1 in the denominator, or in the numerator there. Okay? We're almost there. What would be a better way to write this than 1 over cosine squared? Is there an identity that I could use?
Maybe. Yeah. Probably is.
In fact, it's one you already know. What's the reciprocal of cosine?
Oh, yeah.
Secant. So this is just secant squared.
So you have to do?
And now we're down to a single trig function. You can't do better than that.
It's a lot of steps.
This is a medium one, I would describe this one as. They could be worse.
It's not bad.
Again, it's the place where I see students make mistakes, particularly in this course, is with their algebra and doing things that are not inside of the rules of algebra, right? They make up their own algebra and do something that they can't do, which allows you to do all kinds of kooky things if you can just kind of make it up as you go along. So here we have to be very careful on our algebra. Okay. Let's look at the next one. Again, I like to start by looking for any algebraic things to do. So here we have cosine x over 1 minus sine x minus sine x over cosine x. God bless you. You're welcome. You want to cancel the cosine x's?
Yeah.
You can't do that.
Can't do it.
Oh, it's not.
Because it's not multiplication. Excellent call, yes. Because you cannot reduce across addition or subtraction. Only multiplication. That's an example of an algebraic mistake that like would allow you to do all kinds of crazy stuff that definitely can't do. Sure you can. You have two fractions that are being subtracted. Let's subtract the two fractions. What do you need to have to subtract two fractions? Right, a common denominator. What would the common denominator be in this case? It's not 1. If I had 1 over 2 minus 1 over 3, what would the common denominator be there? 6, right? Because the two denominators are relatively prime, we just multiply them together. If I look at this denominator, I have 1 minus sine x, and the other denominator is cosine x. Is there anything in common between those two? No. So they're relatively prime. So the common denominator is just going to be 1 minus sine x times cosine. Is that okay? Yeah.
Good question. So if it's 1 minus sine x, do we not have to put a 1 minus cosine x? For the common denominator, you just keep it at cosine?
Yes.
Okay.
So the first fraction will multiply by cosine x over cosine x. And the second fraction will multiply by 1 over sine x, or 1 minus sine x over 1 minus sine x. Everybody's okay with that? If you're not, stop and ask, and I'd be happy to try to explain more, or slow down, or give you like an analogy where something with just numbers in it, so it's a little bit easier to see what we're doing. So there's my common denominator, cosine x times 1 minus sine x. Notice that I decided not to distribute the cosine x through. Why would I not want to do that with the denominator? If I'm going to reduce later, the fractions have to be factored form. So I'd have to just undo the distributing that I just did, which you could do later, but I'm just going to not do it here. So then I have cosine times cosine in the numerator, so cosine squared. And then I have negative sine x times 1, so that's negative sine x. Oops. And then I have negative sine x times negative sine x. So that's plus sine squared x. Is everybody okay with how I got this to a single fraction? Let's look for any algebraic thing we might be able to do. Can I combine like the negative sine x and the sine squared x in the numerator? No. Why not?
Well, sine squared and sine squared.
Yeah. They're not like terms. One's squared, one isn't. Okay. Can I reduce the sine x in the numerator and the sine x in the denominator?
Maybe. Well, but there's the one matter.
The one definitely matters, yeah. So we can't do that. We can't reduce part of an addition or subtraction problem. You have to reduce an entire factor or nothing at all, right? So there's no more algebraic things to do, right? There's nothing to combine. There's nothing to reduce. This is all we can do algebraically. So then we go to the identities. Yeah. So take a look at your identity sheet, see if there's anything that jumps up. There should be something that's relatively easy to see that would be good to do here. Give you a second to look to see if you can see it. Anybody got one that they feel like is a good one to try? No, because it's not, the numerator's not factored.
Oh,
Right? Like if you had it factored and you had a sine over cosine in there somewhere, then yes, you could do that. Here's the trick. Cosine squared plus sine squared.
oh, P1.
Yeah. Do they have to be next to each other if they're being added? No, right? Addition is commutative, so it doesn't matter the order in which we're doing the adding. We can move them around so they can be next to each other. How about now? Do we see anything to do here? Yeah. What reduces?
The signs.
The
1 minus sine x and the 1 minus sine.
There you go. Everybody's cool with that? What do we get when those reduce?
Cosine x.
Be careful here. Where's the cosine at?
Well, 1 over cosine x.
There you go. And can we do better than 1 over cosine?
Yeah.
What is that? That is secant.
We don't need to put a 1 over secant, right?
Correct. Correct. Again, that's one of the that's this right here. Right? I guess I could have gone over. Okay. We have, what do we have? 20-something minutes left. Why don't you find a partner and work on the final 4 problems here on this Notes 02 space? I'll kind of move around and help out and ask some questions. This isn't really an assignment. This is just like for you guys to practice. The most difficult part about this topic is you have no intuition as to like what's a good thing to do and what's a bad thing to do. So at some point you just need to like try stuff and see what kind of works out and what kind of doesn't. And really the best way to have that is with somebody else to kind of talk through what you're planning on doing with. So that's the plan for the remainder today. So fire up your old tablet there. You can do it in your tablet or on a scrap sheet of paper or so whatever, wherever you want to do it is fine. I'll move around and take some questions. You can ask some advice. You ask what ifs, did this okay, or what would you do next, or happy to address any of those kinds of things. But at this point, like, you guys need to get your hands dirty and try some of this stuff. You know what I mean? Okay. Let the learning begin.